Now, this is indication for aromatics. One of the things that you can look at is the C double bond C aromatic stretch, which is going to be found in this medium to sharp or medium to strong sharp peak right here, around 1500. And then you can also look for these peaks around 3000 to 28 to 3000, which is the CH3 stretch from this methyl group. And then the hydrogen aromatic stretch from the ring that's right here. So you can, and another thing you can see with aromatics typically is that you see these combination bands. Usually these combination bands is an indication of an aromatic that's in your compound, or at least part of your structure. You could look at these in the fingerprint region, but these indications, the peaks here, are going to be more indicative of what you have in your structure. Now, one of the harder functional groups to distinguish are groups with carbonyls. So we have aldehyde, ketones, esters, carboxylic acids, amides. So one of the things that you can look for is a carbonyl group right here, and this is going to be located around 1700. See if we can find an example here. So on this next slide, you can see there's a carbonyl peak, and this is, you know for sure you have a carbonyl peak if you look at 1700. Now this can shift slightly forward or backwards depending on what type of carbonyl you have. So if you have an aldehyde, ketone, ester, if you have a carboxylic acid, which also contains a carbonyl group, you can immediately determine it or distinguish it from these other four groups because you have an alcohol group in the carboxylic acid, so this OH group, and that's going to be a very strong peak around the 3000 range, and it's going to be a very broad peak. So you saw some sharp peaks for an OH here. This is typically just an alcohol, but for carboxylic acid, this peak becomes more broad and shorter, and is very characteristic of a carboxylic acid OH group. And we'll see a peak of that in a bit. And then for the amide, you can distinguish it from ketones and aldehydes because you have this amine here. So depending if it's tertiary, primary, or secondary, we can look at those amine type peaks in the spectrum, and then also we can look for the carbonyl here. So if we see a carbonyl peak and if we see any amine peaks in the spectrum, we can assume it's some type of amide. For an ester, you have this OR group, so you can assume that there's a single bond CO bond appearing in the fingerprint region, so you can determine the ester from the other ones that way. And you have the carbonyl, so you look for the carbonyl and then look for this C single bond O group here. And then we can go back to show you that. Notice I'll peek here somewhere. It might be further along. All right, here. So we have a C single bond O stretching vibration right here around right above 1000. So this can indicate, and then you should see a carbonyl peak right here. Should be a strong peak right there. And you can determine that it's an ester. For the ketone, you simply have the carbonyl peak there, and then you might have the CC, the what is it called? The sp2 hybridized carbon-carbon bond there. And then for an aldehyde, actually no, this would be just a single bond CC here that you can look for in the fingerprint region. So it's going to be really low, but that still makes it hard because there's a lot of things in the fingerprint region. And then for an aldehyde, you can easily distinguish it from a ketone. And one of these as well, because you have the carbon C sp2 hybridized bond there. So we have sp2, so you can look for this group right here. So you can look for this strong or medium to strong peak right here from the alkene. So this is two examples of two spectra from two heptanone versus butyraldehyde. Now, if we look at the structure here, there's CH3 peaks and then CH2s, and we can see that here. We have the CH3 portion and then the CH2 right here. These are the saturated carbon-hydrogen bonds. Then, of course, we have the carbonyl group, so it should be a C double bond O stretch right here. And then for the next structure, we have butyraldehyde. We can see that there's a carbonyl group, just how in the last structure we have this peak right here. But we can distinguish it from this carbonyl group because there is not only CH3s, because they both have CH3s, but there's what's it called? A carbonyl hydrogen sp2 stretch, which is right here. And you're going to find that in this area, these two peaks. So this is very similar to the double bond, carbon double bond with the carbon single bond H, but we have the oxygen here stretch. So there's a significant distinction with the carbonyl with an aldehyde stretch right here in this region. So when you have molecules that have conjugation, this will lead to weaker carbonyl bonds. So if you have resonance, if you have let's say this unsaturated group, unsaturated ketone, if you have hybrid or resonance, you can move this double bond and move the electrons to the oxygen, and then have the double bond here move over to cancel the charge on the carbon to get this structure. Now it weakens the carbonyl. So these resonance structures indicate that there's a weakening of the double bond here. So due to that, your conjugated system is going to have a lower wave number compared to a ketone that doesn't have conjugation. It's going to be slightly higher. So just note that. One of the easier groups, probably the easiest ones to recognize, are alcohol groups. So we have OH stretching passing 3200. And these alcohol groups, depending on the type of functional group, so whether you have an alcohol or a carboxylic acid, these really strong peaks can be very sharp and intense, or very mildly sharp and very broad. And we'll see that in a bit. And the reason why this OH peak compared to the other sharper peaks is a little bit more broad is because you have hydrogen bonding with other molecules of the same compound. So you can see the hydrogen bonding happening here. It makes these OH peaks more broad, and they become more broader with compounds like carboxylic acids. Very dilute solutions, you have less hydrogen bonding, and so then you have a sharp peak. So you have less of a broad peak in dilute solutions because you have less hydrogen bonding. The more concentrated solutions, you have more hydrogen bonding occurring, so then your peak it's going to become more broad. And in this structure, we know we have if it's an alcohol, we have a carbon bonded to the oxygen as well. We can also see that in the fingerprint region. You get this medium sharp peak right here for the CO stretching bond for a primary alcohol. So for carboxylic acids, you have two functional groups that you can look at. So this is the structure right here. We have an alcohol, an OH group, and we have the carbonyl. So we can see that in the IR spectra, we have the carbonyl. And then we also have, with the same spectrum, the alcohol, or the OH group from the carboxylic acid. And this is very much more broad than compared to the last structure, where this is a little bit more sharper and less broad. And that's because on the molecule, you have 2 points of hydrogen bonding occurring. And if you have a more strongly concentrated solution of carboxylic acid, this becomes more broad. So this is an ether, dibutyl ether. And you can compare, this should have two types of characteristic peaks. You have the CH3 peaks for the sp3, and then the CH2, it's kind of lingering right here. And then you also have the CO single bond, which is in the fingerprint region. This is the sharp peak for it. So here, the most characteristic is just the CO single bond stretch. So ethyl butyrate and methyl benzoate. So in this structure here, we see a carbonyl. And then we see a carbon single bond O. So we see that carbon single bond oxygen stretch right here. We also see the carbonyl in the structure, so we should see a carbonyl. And then we can see we obviously have CH3, sp3 stretching happening. And then a portion of this is from the CH2 right here. Now in methyl benzoate, we have multiple things happening. We can kind of have combination bands right here from the aromatic that's occurring. And then we also see two other things in addition to the phenyl, to the benzyl. We have the carbonyl, and we have the ether, which is going to be in the fingerprint region for the C single bond stretch. And then we also had the aromatic, if you remember from the aromatic section, this double bond C. So carbonyl, CH2, CH3, these are a little bit shorter. And then the CO single bond for the ether portion. This is the ester technically. Now, I think amines is the last one. So amines, you can distinguish them from each other. So if you have primary, secondary, and tertiary. So the primary amines give two peaks around 30 to 34. So if you have a primary, you have two peaks. And then if you have a secondary, so as in this structure here, you have only one peak. So you can distinguish primary from secondary in that way. Now, if you have a tertiary, you don't have any peaks in this region. You'll have a carbon single bond N that you can look at in the fingerprint region. So just a few practice ones in the chat if you want to post it for a bonus point. What are the two functional groups present here? You can say it in the mic or you can put it in the chat. Okay, so what we have here, I can move. What we have here is, if we want to talk about functional groups, we have a carbonyl here, and then we have the OH group here. Now, if you want to be really specific, this is a carboxylic acid. So I think most people got it right. They had at least the two functional groups. If you got both, you get a point. If you either get both right, or if you get if you say carboxylic acid, then you automatically get it right.